So far we have seen measurability concepts. Today we will be looking at integration of positive functions. So, we will start with integration of simple functions and then go on to positive functions. After we define integral for positive functions and look at some properties of that, we would extend it to real valued functions and complex valued functions. So, we start with positive function. So, integration of positive functions. So, our setup is always we have a space X, we have a sigma algebra and we have a measure. Measure remember is a countably additive measure. So, script f is a sigma algebra of subsets of X, mu a countably additive measure, countably additive measure. We will be defining integration with respect to mu over the space X. So, let us start with a simple function. So, let S be a simple function which takes values in 0 infinity, be a simple function. Simple function, remember simple function is a measurable function whose range is finite. So, I can write S of x to be equal to summation alpha j chi e j j equal to 1 to n, right. What are EJs? EJs are measurable sets. So, they are in script f, okay. Alpha j are scalar. So, I will take this to be in 0 infinity because I am taking a positive simple function. I want to define the integral of S with respect to the measure mu, okay. So, define the integral of S. So, this will be denoted by integral over x S d mu. This is a symbol integral over x S d mu. This is defined to be if S is given by this summation j equal to 1 to n alpha j chi e j, then the integral is simply summation j equal to 1 to n alpha j mu e j. So, let us just look at it again. Suppose my simple function is simply an indicator function. I take indicator or characteristic function of E. E is some set in script f measurable, right. So, our definition says that integral over x S d mu, this is simply mu of E, measure of E. So, this is the crucial definition. So, if S is given by the indicator of E, then the integral is simply the measure of E. And when you have more values for S, so that is same as saying it is a linear combination of measurable sets from script f, then of course, the integral is going to be the sum of integrals of each piece actually. So, we are forcing linearity in some sense here, but alpha j mu e j. So, think of simple functions like step functions, then this is what you will do in the case of Riemann integration, right. Suppose my simple function is like this, the integral of this, the Riemann integral of this is simply the value. So, let us say this is alpha 1, alpha 2 and alpha 3, you will multiply alpha 1 with alpha 1 into measure of this length of this interval, then you take this interval and multiply it with alpha 2, then you take this interval multiply with alpha 3 and then add up. So, that is how you get the area under the curve, right. So, this is the integral value of the integral of the step function alpha 1, alpha 2, alpha 3 taking values in these intervals. That is precisely what we are doing, except that now we have these sets E j's which are more general than more general than intervals. Okay, so that is the concept we needed. We needed length for sets like E j, which is given by the measure of E j. Okay, so that is how it is defined. Now, using the simple functions, one can use this to define integrals of positive measurable functions. Okay. What does that mean? You take a measurable function which takes values in 0 infinity and you define integral of f d mu to be, well, what you do is you take the supremum of all those simple functions less than or equal to f and you take the integrals of these simple functions. So, remember these are defined, the integral of simple functions are already defined and we are taking those values and then taking the supremum. So, in Riemann integration, if you recall, in Riemann integration we looked at certain upper Riemann integrals, that is by taking the supremum over certain partitions and taking the integrals. Those integrals are precisely the integrals we just talked about, right. We are integrating a step function over an interval. You will get an expression like what we have already seen. So, if S is summation alpha j chi E j, then integral over x S d mu was summation alpha j mu E j. So, this is more or less like a Riemann sum, right, similar to Riemann sum, okay. And then you are taking supremum over all such simple functions less than or equal to f. So, remember this is already defined using this one, and then you take the supremum over all simple functions less than or equal to f. So, this is what defines, so this defines integral for positive measurable functions. So, remember that. So, I should also tell you that in this, here the convention is that infinity times 0 is 0. So, some of the measures can be infinity, right. We will look at examples, so it will be clear, but if the simple function takes the value 0 there and if the set has infinite measure, it will multiply to be 0. So, let us look at some examples. Okay. So, example, easy example. So far we have seen only counting measure as a measure. So, we will simply look at that. So, let us look at natural numbers. So, this is my space X, the sigma algebra is the power set. So, all sets are measurable and mu is the counting measure. Okay. So, what would be a simple function? Simple function is something which takes finitely many values, right. So, I can define S to be, so let us say S of 1 to be some value, let us say A1, S of 2 A2, and it could be 0 for some values and so on, but it can take only finitely many values. So, I will have to stop at some point Sn is some An and then everything else is 0. So, Sn plus 1 equal to Sn plus 2 equal to etc. is 0. So, how does this look like? So, the simple function S is simply S of x, I can write as on 1 it takes the value 1. So, it is A1 times indicator of the set 1 plus A2 times indicator of the set 2 plus etc. plus An times indicator of the set n, right, plus 0 0 0 0, right. So, it does not So, this is like Aj chi Ej. So, according to our definition, the integral of S d mu is nothing but this is. So, I can write this as integral over x. So, the function looks like this Aj chi indicator of j. This is my function S d mu. This by definition is summation j equal to 1 to n. You multiply Aj with the measure of the set. So, that is measure of the singleton j, but the singleton j has just one element. So, the counting measure is simply 1, right. So, this is summation j equal to 1 to n Aj. So, you see summation is an integration. Okay. So, what this implies is that summation is actually integration, or more generally integration is generalized summation. You are adding up certain things. Now, in the same example, let us look at what happens if I take a function. So, again x is n, this is the power set. So, if the sigma algebra is power set, any function is measurable, remember that. Mu is the counting measure, and let us take a function f from x to 0 infinity, which is measurable. So, any function. So, this is measurable would mean any function, right, because the sigma algebra is the power set. I want to find out the integral of f. What is integral over x f d mu? Okay. Well, what is this? This by definition is supremum over all simple functions less than or equal to f, and then you integrate the simple function. This we know how to do, and you take the supremum, right. So, how does a function look like? Function on n is simply f of 1, I know what it is, f of 2, f of 3, etc., right. So, this is the collection of values of f, and that defines the function f. Now, how would a simple function look like? Simple function takes values, only finitely many values, and so it would be, and it has to be less than or equal to f, right. So, the maximum value of s of n will have to be less than or equal to f of n. Okay. So, let us take these functions. So, let us define s capital N of x equal to f of x if x belongs to the first n elements, okay, up to n, okay, and 0 otherwise. Okay. So, I am taking a particular simple function. So, this is a simple function, non-negative, because f is non-negative. Okay. What is the integral of Sn, this simple function, with respect to the counting measure? So, we have seen this earlier. This is simply the values of Sn added, and that goes from j equal to 1 to n, and you look at f of j. Okay. But we are supposed to take the supremum over such simple functions less than or equal to f, right. So, such a this Sn is of course less than or equal to f. Now, if I take the supremum, of course, this is going to be less than or equal to summation j equal to 1 to infinity f of j. But I can go as close as I want to this summation by taking large n's. If this converges, if it does not converge, it is going to go to infinity. So, this tells me that the integral of f over the space x, where x is n, this is simply the summation. So, the infinite sum is actually the integral. So, the moral of the story is an infinite sum is the integral with respect to counting measure. Okay. So, let me rephrase it. Suppose I have, suppose we are considering, okay, so consider summation aj, j equal to 1 to infinity, okay, aj positive, because we are looking at only positive functions right now. I want to say this is actually, this is integral over x f d mu for some function f, and mu counting measure, where this whole space x is simply n, the natural numbers. Well, how do you do this? You simply define f to be by f of j equal to aj, right. Then integral over natural numbers, that is my whole space, f d mu, mu is the counting measure and the sigma algebra is the whole power set. This I know is summation j equal to 1 to infinity f of j, which is summation j equal to 1 to infinity aj. So, any infinite sum is actually a integral. Now, before we go further, we look at some properties. Okay. Properties. Okay. 1, 0 less than or equal to f less than or equal to g, then integral over x f d mu is less than or equal to integral over x g d mu. Of course, all these are measurable. So, these are measurable functions, otherwise the integral does not make sense. Well, this is trivial because if, so this I will say is trivial if 0 less s less than or equal to f, s simple, then 0 less than or equal to s less than or equal to g. And so, you will be taking supremum over a larger set for the definition of g, and so it will be much bigger than this set. 2, if f is non-negative measurable and I have a constant c, then of course, c times f is also measurable, right, and the integral of c times f with respect to the measure mu would be, this is equal to c times integral x f d mu. So, always remember we start with the triple x script f mu. Okay. We have a space x, we have a sigma algebra of subsets of x, and mu is some measure, countably additive. And we defined integral of simple functions, taking supremums we define integral of positive functions, and we are looking at the properties of that. So, this is called the monotonicity property. So, recall that we had monotonicity property for the measure, right, that is same as this. So, let us just recall that. So, if A is contained in B, then mu of A is less than or equal to mu of B, right. So, remember mu of A is the integral of the chi of A with respect to the measure mu, and we are saying that is less than or equal to the integral of chi B, right. That why is this true? Because chi A is less than or equal to chi B, because A is contained in B. So, that is simply the monotonicity property for indicator functions, which is true for all positive measurable functions, that is what we know. Okay. So, this is also trivial, I will leave it to you. Third one, if f of x equal to 0 for every x, then integral of f d mu is 0. So, this is even if mu of x is infinity. Okay. So, remember the convention is that 0 times infinity is 0. Fourth property, if mu of x is 0, then integral over x f d mu is 0. even if f of x equal to infinity for every x. Okay. Why is this true? So, let us do the fourth property. Suppose mu of x is 0. So, total measure is 0. Then let us take any simple function, let f be any simple function which can be of course written as simple s of x equal to alpha j chi a j, j equal to 1 to some capital N, finite linear combination of indicator functions, that is what simple function is. I am assuming this is less than or equal to f. Now, integral of f is the supremum over certain things, right. So, supremum over s less than or equal to f, integral over x s d mu. Okay. So, I want to calculate these things and then take the supremum. So, if I look at integral over x s d mu, well, what is the definition? This is simply j equal to 1 to n alpha j mu a j, that is our definition. But what do we know about mu a j? Mu a j is less than or equal to mu of x, which is 0. So, all this is 0. So, for any simple function s less than or equal to f, the integral of this is 0, and so when you take supremum over this, you will get 0. So, even if f of x is infinity for every x, if the total measure is 0, then the integral is 0. Okay. So, now let us just slightly generalize this notion. So, I have this space. So, recall in the Riemann integration we integrate over any interval we want, not just the whole real line or the whole space. So, we want to do the same thing here. I want to define, if I take some measurable set in f, I want to know what is this, can we define this? Well, so one definition is this. So, let E belongs to script f, f positive measurable, then integral over E f d mu. Well, we do the natural thing. So, we know how to integrate over the whole space, but I want to restrict f just to E. So, I simply multiply f with indicator function of f, indicator function of E, and then integrate. So, what is this? This chi E times f is a measurable function, is a measurable positive function. So, I know how to integrate it, right. I look at all simple functions less than or equal to this, integrate and then take the supremum. So, that leads us to two definitions in fact. So, let me give this as an exercise, I will explain what that is. So, you take x f mu and let us take some set in script E, script f. Define the following sigma algebra, define script f sub E. What is this? This is the collection of all sets in script f, but which are contained in E. So, now it is like the whole space is E, we are not going out of E, we look at all subsets of E which are measurable. Okay. So, prove that this is a sigma algebra of subsets of E. Okay. And define mu sub E of A equal to mu of A for every A in script f. Okay. Then mu sub E is a measure. Of course, this is a measure because mu is a countably additive measure. So, mu sub E is also going to be countably additive, except that now we look at only sets which are contained in E, we are not going out of E. So, now we have a triple E is my whole space now. I have script f sub E which is a sigma algebra of subsets of E, and I have a countably additive measure. So, whenever we have a triple, we know how to define the integral. So, I can define the integral using this, right. So, I will have integral over E f d mu sub E. correct. This I know how to define. If I have a space, I have a sigma algebra script f and I have a countable additive measure, then I know how to define this. Okay. Check that this is equal to integral over x chi e times f d mu. That is our original definition, right. So, this definition and this definition are same. So, we could have started with any subset of x which is measurable and defined integration over that set, or we could start with the whole space and then multiply f with any indicated function, so that we can restrict everything to that particular set.